They say the first step is the hardest, but once you have taken that leap, building a strong foundation seems like a breeze, right? It's wrong. It is about knowing where to step, how to build, and why you are doing it in the first place. What are those essential building blocks? The cornerstone concepts that will support your journey. It is like laying bricks without knowing the blueprint. You need direction, purpose. Well, with differential geometry, taking the first step is crucial. Also, knowing the objective why you are taking this first step makes your journey more interesting and goal-oriented. In today's video, you will be learning the first step in learning the mathematical concepts, which book to consult, why you are learning, and its significance to mathematics. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to part 2 in this series of videos on how to learn differential geometry. First, here is a quick recap for those who have missed my first lesson, although I have given it in the I button and you can find it in the playlist. So in the first video, what we have done is that, although that was an introductory video, we learnt about what is differential geometry, taking ahead the meaning of the two words differential and geometry. We came to know the reason that why do we need to use calculus, and especially using those calculus on the curvature or knowing the internal structures of geometry. Thereby we came to know that what are the best books in terms of calculus, the book recommendations with Piskunov and Thomas Calculus, and I gave a complete understanding of these reviews of the books, which book to read, what are the essential steps, and so on. You can find this on the I button and go to the first lesson of learning differential geometry. Then we also learned that what kind of geometry that we need. That means after learning calculus, what kind of geometry you need. You need to have an understanding about spatial reasoning, relationship between spaces, analytical thinking, and so on. For that, I suggested some of the books, but the first book was to understand how the transition took place from Euclidean to non-Euclidean geometry. Marvin J. Greenberg's this book would serve that purpose. Also, you learned in the first lesson that why you should learn differential geometry. What is the reason that it would actually give a kind of an understanding to other branches of mathematics and physics. Also, because differential geometry and topology are similar concept which overlaps with each other. What is the difference and why we learn differential geometry and when we look over to topology. We also came to know what are the mathematical prerequisites in terms of learning differential geometry, and the most important thing is that because differential geometry depends on a proof-based mathematical system, I gave at least 2, 3, 4 books and what are the best books in recommendation for learning proof, because it is very true that learning proofs would take some time. So what are the book recommendation? So we paused our video in this part of our learning that differential geometry can be started either using curves and surfaces, or we can use manifold. And I told in the first video that we will actually establish the fact that why do we start with curves and surfaces and not with manifold, and this is where we actually stop. So we will start today's video from here, that why we are learning curves and surfaces, and I will show you logics and justification behind that, and then we will go ahead in the core part of the learning. So first of all, when we talk about curves and surfaces, the first thing is that what are the mathematical prerequisites? To be very honest, not much. What you need to know is that a strong foundation of multivariable calculus, which includes partial derivative, vector calculus, and multiple integrals, and a very good understanding of linear algebra. Now, if you're wondering that what book to select, which part of linear algebra or calculus relates to differential geometry, this is the video which I made it, and you can go ahead and check onto that, and thanks to you because it has got a good number of views. So this video actually contains all the necessary books, the recommendation, as well as a complete understanding of differential geometry. What are the books that you should learn, what books carries the complexities, what are easier books to go ahead for a beginner, every single details. So the prerequisites are pretty simple. Good understanding of multivariable calculus along with linear algebra. Now what we do is that we start first with curves and surfaces. Now, as I told you in the first lesson, we paused that we need to look over curves and surfaces and not manifold. First, let me tell you, because in mathematics, everything should come up with a proper reason, that why are we taking curves and surfaces and why not manifolds? And you see, you can select any book in differential geometry. The first few chapters are either starting with manifold and curves and surfaces. However, I am going to suggest you to start with curves and surfaces, and these are the reasons. If I talk of the conceptual complexity, then curves and surfaces have complexities which are much more lower and manifolds are higher. So the reason for learning is that curves and surfaces are involve more intuitive and visual concepts, which makes the complexity lesser. The second part is that mathematical prerequisites, curves and surface, requires just a basic calculus. Obviously, PDEs will be required a lot, but in manifold, you need a lot of advanced calculus, I mean to say topology, abstract algebra, etc. So that is the reason for learning, is that it requires less advanced mathematical knowledge. If I talk of visualizations, these are 2D and 3D more or less, but in manifolds often higher dimensions are required. I mean to say, you need to think in higher dimensions, so that is why it becomes difficult. So visualizing curves and surfaces in 2D and 3D helps build intuition, and you can later extend it once you learn these concepts into manifolds. So these are the three reasons. Complexities are much more lower, mathematical prerequisites are easier, and visualization is also easy. Next, you see that if I consider the learning resources, curves and surfaces have more tangible books, notes, etc. are much more available. These are availability learning resources are high, abstract concepts and spaces. Learning the more concrete concepts of curves and surfaces helps to build the abstract thinking which is required for understanding manifolds. So manifolds, yes, the learning resources are although high, but learning the concepts of curves gives you a better understanding. In terms of problem solvings, it builds the foundational problem solvings and it requires advanced problem solving. So the reason for learning is that developing problem solving skills with curves and surfaces create a very solid background which you can take up later to solve problems on complex manifolds, etc. Now, if I talk of the abstractness, obviously curves and surfaces are less in terms of abstract, manifolds are high, and the reason for learning is that it focuses on concrete geometric objects. I mean to say curves and surfaces. Manifolds are pretty abstract, sometimes becomes difficult to understand. Foundation for manifolds, it is strong, obviously. For manifolds, it will be not available because manifolds are manifolds. So concepts learned in curved surfaces also helps in learning the manifold theory. Theoretical founding, it would create a very good solid grounding in geometry, and it actually builds on the theory of curves and surfaces. So the last reasoning would be understanding curves and surfaces are essential for grasping the local and later the global properties of manifold, which takes into topology, which we are not considering now. So point number one is that in this part of the video we understood that why we are going for curves and surfaces with some real solid reason for understanding, reasoning, complexities. All these are fairly easier. Now as we go ahead in differential geometry in this series, you will see I will be explaining more abstract concept, but first thing that we should learn, and obviously there's a reason for this to learn, is called parameterization. Now, you might already have parameterized certain concepts in terms of basic algebra, trigonometry, etc. But what is the basic idea and the deep underlying sense of parameterization, that we will cover in this part of the video. So first, here is a definition that parameterizing is basically a way of describing a curve. Instead of representing a single equation, we can use parameters so that we can actually use more than that. So let me show you an example. So let us take a simple example of a circle, and the equation of a circle is centered around the origin with radius r, and this can be expressed in both, I would say, x and y terms. If I express in this term of the variable. So what happens is that this is not a parametric form, but the equation of the circle originally x squared plus y squared equal to r squared. This is not a parametric form. However, to use the parameter, we introduce a parameter usually denoted as t, which can be thought of as a function representing angles in radians. So here you can see x equals to r times cos t and yt equal to r times sin t. So what happens, t is basically the parameter and it usually represents the angle around the circle. So C is the radius. I have not drawn that circle, but as you can easily understand that it represents the angle from the positive x-axis, and this t varies from 0 to 2 pi. That means the points x and y that traces out a circle, it will vary from 0 to 2 pi. So this is a very simple example, but the concept of this can be extended to much more complex shapes and curves. So this is what as the angle and the t varies and the trace of the circle would be going round and round. So that means it can be taken any value rather than just putting up a single equation and a constant value. So what you can see from here, what we can say is this one, that parameterization actually allows us to describe more complex paths or complex shapes in a flexible way, because as t varies the things changes, etc. And it also simplifies the analysis and calculation of properties, because we can, why it simplifies, because we use expressing coordinates. Now let us see an example. So y equal to mx plus b or mx plus c, this is, we know that is an equation for a straight line, but this works, it can be limiting in the sense it does not easily represent a vertical line where, for example, m can be undefined. So if we parameterize and we use this one, x equals to at plus c and y equals to bt plus d, the question is that it becomes simpler. Now why it becomes simpler? Here you can see that these are the following reasons. It can handle all the cases. By changing the values of a, b, c and d, we can create different lines, and we can introduce a time parameter such as t in order to calculate the motion of a point along the line, which I have not done, but it can be done. So further example, for example, y equal to 2x plus 3. Now to represent this parametric form, what we can do, we can choose something like this. Y equals to 2x plus 3, x equal to t, and y equal to 2t plus 3. And this t actually goes back to this. So by changing the values we can get. So from here what we can deduce is this, that parameterization offers a more flexible and versatile way to represent geometric objects and makes it a fundamental tool in differential geometry and other fields. So the first thing that you need to learn when you're taking the first initial baby step for differential geometry is parameterization. You can make further parameterization using complex mathematical equation, but the basic idea of parameterization is this, and this will give you an objective that why you're learning parameterization and why the books are talking of parameterizing different types of curves and equations. The second thing which comes across are called tangent lines and tangent planes. I know you have heard about tangent lines frequently, but this is basically what is a tangent line, a line that just touches or just kisses the curve at that point. So it has the same direction as the curve at that point, and it actually represents the instantaneous direction of the curve. Now if I talk of a tangent plane, it is more or less similar, but it is something different. As you can see, it touches the curve, and here that just touches the surface at that point. It has the same orientation as the surface at that point. Now tangent line I am not going to explain because these are done in class 7, 8 and 9. But tangent plane I would like to explain with this kind of a diagram. In the next part of the video, let me zoom this diagram so that it looks better. Right. So here you can see, what I can tell is that let P0, which is x0, y0, z0, y, obviously because the surface it has got a 3 dimension, let it be a point on a surface S. Now this is a point which I just highlighted in red, and this is the surface S, this one, and let be it on a surface S, and C be any curve. So this is the one, this is the curve. So C be any curve which is passing through P0. So now what happens is P0, so C be any curve passing through P0 and it lies entirely on the surface S. The thing is that if the tangent lines of all such curves, remember I'm talking of one curve C just to make things easier. So let me draw it once more. This is the line, this is the surface, this is the dotted line. And what I'm saying is this, that if the line, it is lying on the plane, and it lies in the plane entirely, and if all the tangent lines to all such curves C at P0 lie on the same plane, then this is called a tangent plane, and this is called the tangent plane to S at P0. So this is important. I take a point P on a surface S, and I will take a curve C and if the tangent lines to all such curves which are passing C at P0, if it lies on the same plane, then this plane is called the tangent plane to S at P0. So from here we get a remarkable statement which I would like to explain and take it further, is this one. For a tangent plane to a surface to exist at a point on that surface, it is sufficient for the function that defines the surface to be differentiable at that point. So it should be something which is differentiable at the point. Now I will try to take up this statement and explain, because this would bring up some great, I would say, mathematical details. So I will take this one, and what I would take is that what does the statement tells? The statement actually tells that if a function which defines a surface is differentiable at a specific point, remember that a function defining a surface is differentiable at a specific point, then a tangent plane can be drawn at that point. I will explain it one by one. First is that we know what is a tangent plane by now, that a plane that touches the surface at a single point and shares the same slope. We also know what is a differentiable function. What is a differentiable function? It is differentiable at a point if its derivative exists at that point. So for a multivariable function, this means that the partial derivative exists and are continuous at that point. So from this tangent plane and differentiable function, we get three important results. Number one is that a differentiable function has well-defined partial derivatives, obviously. And these derivatives represent the slope of the surface, x and y, so on. The second thing that we get is that at a small scale, a differentiable function can be approximated by a linear function. We will look into that using this as partial derivative, and this is the essence of what we call linear approximation. The third conclusion that we get is that the tangent plane is the best linear approximation of the surface at that point. This is the best linear approximation of the surface at that point. Why? Because since the function is differentiable, this approximation is accurate, and hence we can say that the tangent plane exists. Now this is all simple English, but let us look into the mathematical notations to make things much more simpler. So a surface, if I take on R3, can be described by a differentiable function f of xy. This means that the surface can be represented as z is equals to f of xy. And if f of xy is differentiable at the point x0 and y0, what does it mean? It means that f has well-defined partial derivatives with respect to x and y at x0 and y0, and these partial derivatives are denoted as this one, f of f sub x x0 y0 and f sub y x0 y0. Simple. Now the tangent plane to the surface at the point which is this one, x0 and y0, is the plane that best approximates the surface near the point. So mathematically, the equation of the tangent plane using partial derivatives, it can be written as something as this. So let me again repeat if the concept if it is not clear once more. So if there is a surface on R3 which can be described by differentiable function f of xy, this means that the surface can be represented as z equals to f of xy. If f of xy is differentiable at a point x0, y0, it means that f has well-defined partial derivatives with respect to x and y at x0, y0. These partial derivatives are denoted as f of x x0, y0 and f sub y x0, y0. The tangent plane to the surface at the point x0, y0, f x0, y0 is the plane that best approximates the surface near that point. Mathematically, the equation of this tangent plane with partial derivatives can be written as this. So from here what we can tell that the existence of the partial derivatives f sub x and f sub y at x0, y0 implies that the function f is locally linearizable around x0, y0. Obviously, if it is that, then it should be locally linearizable. Let me again tell the existence of partial derivatives f sub x and f sub y at x0, y0 implies that the function f is linearizable around x0, y0. This linearization precisely is the equation of the tangent plane. Hence, the differentiability of f at x0, y0 guarantees that these are local linear approximations. So here we get. So if this is at x0, y0, it guarantees that this is a local linear approximation. So few things which quickly makes up from this mathematical equation is that, remember that the key point is this, but however there are a few points which I would like to tell. One is that differentiability on a point of a surface means that the surface can be locally approximated by a plane at that point, number one. Second is that if a surface is differentiable at a point, it ensures that the surface is smooth enough, obviously. Third point, smoothness here refers that the absence of any sharp corners or discontinuities. Fourth point is that smooth surface allows for a well-defined tangent plane, which is crucial for many applications in differential geometry. Fifth is that a well-defined tangent plane can only exist if the surface is differential at that point. And the tangent plane provides a linear representation of the surface behavior near the point. So in summary, we can say that differentiability is a key property that ensures the surface is smooth enough to have a tangent plane, avoiding sharp corners or edges or discontinuities that would disrupt the linear approximation. This is actually what it actually comes up. So here again, if you look into this mathematical statement which we did, in summary, for a tangent plane or a surface to be defined as z equals to f of xy, to exist at a point which is this x0, y0, f x0, y0, it is sufficient that the function f is differentiable at x0, y0. The differentiability condition ensures that the function has a linear approximation, which is exactly the equation of the tangent plane which we have seen earlier. So this actually shows the basic idea that why we need a tangent plane and how it actually happens. So from here, the question comes is that we understood all those mathematical tricks and how it happens, the partial derivative. Question is that why should we study? I mean to say, what is the reason? Does it create any sense? Obviously, for a tangent line, for a curve, the tangent line at a point provides the best linear approximation. For a tangent plane, this is the best linear approximation to the surface. This is the curve, this is the surface. And what it shows that the existence of tangent lines and planes is a sign that curve or surface is smooth and differentiable at that point of tangency. So two things come up, very important. Differential geometry studies the behaviors of curves and surfaces. Tangent lines and planes are tools to understand and analyze these properties. In broader context, when we will move into manifold, we will see that tangent space at a point on a manifold is a generalization of the tangent plane. And the tangent space is essentially used for defining concepts like vectors, fields and differential forms, which we will take up later. So the answer is that it provides a simplified analysis, obviously, because tangent lines and tangent planes provides a kind of a simpler understanding. Second is that it helps in understanding geometry of curves, surfaces and orientation, and it has got huge number of applications. For example, computer graphics, engineering and so on. So from here what we can see is that you see this tangent line and tangent plane. Both tangent line and tangent planes are manifestations of the same underlying principle, which is called linear approximation. So what is linear approximation? It is just essentially using a straight line to estimate the value of a function at a specific point. So what I'm trying to tell is that they both serve to approximate the original geometric object using a simple linear object at a specific point. In both the cases, the tangent line or plane captures the local behavior of the curved surface near the point of tangency, and this local behavior is what defines the concept of tangency. So this gives us a very clear idea about linear approximation and how it is related to tangent line and tangent space. So here you see, in case of a one-dimensional case, for a function of one variable, the tangent line is the best approximation, and for multi-dimensional case, tangent plane. And here is the final, I would say, a kind of an understanding. The linear approximation is a powerful tool used in mathematics and its applications, providing a good way to understand and work with complex functions. This technique is fundamental in many areas of science, engineering, and so on. So now you understand that why the books do explain, and we will come to the best books which explains those tangent lines and tangent planes and so on, why it is so, what is the reason, and ultimately it basically speaks of the same concept of tangency. In the next part of the video, we will quickly look into the third most important concept, which is called arc length. So arc length is basically a distance measured along the path of a simple term. So you know about arc length. I think these are read in primary school, so I'm not explaining. However, in terms of differential geometry, it becomes important. So S equals to theta r, and for angles in degrees, this becomes a kind of an understanding. So studying the arc length of curves is fundamental in understanding differential geometry or geometry of curves and surfaces. Also, arc length is crucial for parameterizing curves, and in differential geometry the arc length is often used because it leads to simpler and more natural description of curves and surfaces. So we will take step-by-step approach. We are not going into all the complexities on this video. So we will come to the next part, which is what is the best book that explains. But before coming to what is the best book that explains, I will first like to tell you in the sense that finally what are the concepts that it actually leads into. So you see that parameterization is basically, which means that it allows to represent curves and surfaces is using equations which involves one or more parameters. So I'm summarizing now so that before going to the books we can understand. Second is the tangent line and tangent plane, which we actually got into that, which is basically the best linear approximation to a curve at a surface at that point. And third is that we got what is arc length. But here is something important. I have written that arc length is invariant under reparameterization. What do I mean by that? Is that this means that no matter how you describe a curve mathematically, the length of the curve remains the same. So intuitively think of a curve as a physical object like a piece of a string. You can describe the string in different ways. For example, its length, the time, by some other parameter, but the physical length of the string itself doesn't change. I'm not going into cutting and gluing, those are different. So mathematically this can be shown by using the integral formula for arc length and applying the chain rule for the derivatives when changing parameters. The result is that integral simplifies back to the original arc length of the formula. We next look into what is a curvature, although this thing we have not covered in this video, but I will be covering. It measures how much a curve deviates from a straight line and uses second derivative for parameterization. Then comes another effect which is called torsion, which tells you how much a curve twists out of the plane of a curvature. And this provides a complete description of the geometry of space, curve, etc. Also, it will provide something related to the stability and behavior of structure and materials. And finally, geodesics, which are the shortest path between 2 points, and they generalize the concept of straight line to curved spaces, and we talk about geodesics a lot into Einstein's general relativity. So these three portions, remember, we have not covered, but these are the essential steps. So the first book which I would recommend is this one, Differential Geometry of Curves and Surfaces by Manfredo P. do Carmo. And this has got a very good rating. Now you might say that why I'm not taking other books. There is a reason, because we have learned the first steps. I need to tell you what are the first steps and what are the books that basically covers the foundation. Here you can see this one I have highlighted, although it contains a lot of other things, but the initial steps are remarkable. Parameterized curves, arc length, vector products, change of parameter, tangent planes, oriental surfaces, and so on. You can read the further part of the book, but this part, curves and regular surfaces, what we are discussing is covered. The second book is this one, Francesco Tovena and Marco Abbat's Curves and Surfaces. I have cited in numerous occasions about this book. However, I'm not going into reviewing this book, but you can just see that local theory of curves, arc length, curvature and torsion. We talked about torsion, isn't it? Local theory of curve, geodesics, Gauss-Bonnet theorem, which I will cover up in the next part of the video. In the next video, all these are covered. So it's a very good book to take up the first step. Now the second one is Christian Barr's elementary differential geometry. I have highlighted only those portions which you have dealt: curves in Rn, plane curves, tangent plane, curvature, vector fields, geodesics. All these things are covered. So this is also very good. Remember, I'm not reviewing the book, but I'm just telling you these part of the learning is well covered in this book. And the next book would be very good by Thomas Bancroft and Stephen Lovett's Differential Geometry of Curves and Surfaces. So you see, everywhere it is telling curves and surfaces. So nowhere we are going to manifold, and that is the main point which I'm trying to prove in this video, that before going into manifold, why don't we learn this? So here also I have highlighted in red parameterization, curvature, parameterized surfaces, tangent planes, geodesics, Gauss-Bonnet theorem. The last and the most favorite one of my book is Andrew Priestley's Elementary Differential Geometry. It contains a lot, and it is a first step. It is elementary differential geometry, doesn't speak much about manifold. So here you can see what is a curve, arc length, reparameterization, simple closed curve, what is a survey, tangent plane, geodesics, length of curves and surfaces, and level surfaces. Everything is covered in details. So what is the point of showing is that you don't have to purchase or get all of those books. Any one of those books will give you a solid understanding in terms of understanding the first step, that is curves and surfaces, and then we will go into the further complexities. So the final summary is this. These are the initial steps to start learning differential geometry, because based on those, more complex concepts are built. However, if you make a very good strong foundation of these concepts, this will help you in ensuring a smooth journey in the rest of the complex differential geometry world which is waiting for you. So that's it for today's video. I think that you have really enjoyed this part. Thank you very much for taking up time and watching this video. Please do subscribe by hitting on the subscribe button and click on the bell icon to get all the notification from Physics for Student. This is my email ID, and this is my other channel on General Theory of Relativity, which you can subscribe, and you can follow me further on my Facebook, LinkedIn, Instagram, and Twitter account. So we have covered the second part of how to learn differential geometry. However, in the context of curves and surfaces, few concepts are still remaining, which I will cover up very soon into the third and the subsequent videos of this series. Thank you very much, and may the good Lord be with you.